Good morning, everyone. Let me start off by going over what's on my website here. If you're on Teams, you've been pulling these notes and assignments from my website on the spring review page. But if you're in class, you're just picking up these handouts. So today, we're going to be going over parts of all these worksheets here. I may not be able to get through everything, but I will. Keys are there, and the videos are available as well for homework number 9. So you're going to be, we'll be working through these, and if you're on Teams, you probably want to have these sheets available so that, yeah, I'll be kind of jumping back and forth between these different worksheets. Yesterday, most of you turned in your assignment. So I know that there was an issue with, not issue, but just a limit in a number of pages that teams can take. And so some students reached that limit, and then they sent me the rest through email. So that's fine. If you haven't done, or if you've turned in a part of it, but then the other part, because of that restriction, you can send it to me through email. I won't take off any points. Some of the students, they just took photos 2 pages at a time, and so they're able to be within that 10-page limit. But for those of you who have not turned it in, you're still, I'm still giving you the majority of the credit, but so you can just turn it in through email. The assignment on Teams is closed, so you can just send me any late assignments through email or through Remind. But if you do through Remind, make sure you send me 1 photo per text, right? If you try to put all the photos under one text, I'm only going to see like 1 of the pages or 1 of the texts, not all of them. So 1 photo per text. If you want to do 2 pages per photo, that's fine. Okay, so as soon as you turn that in, I think this weekend I'll be able to clear up a lot of the grading that I haven't entered in. So tomorrow's your quiz, okay? And I'm putting together this morning review worksheet that I feel like is going to be a very good representation of what your quiz is going to be like. So I really encourage you guys sometime today, this afternoon, evening, to work through this morning review. But if you can, maybe if you can hold off until later this afternoon, there's some tweaks that as I'm working through the key, I realize I need to go and make some adjustments. So I'm working on the key. I'll get that up and running, available by this afternoon. But I want to have 2 sessions going over this morning review, and both will be recorded. So the first is 4 to 5 p.m. on Teams. So I'll go through each of these problems in detail. If you want to join me on Teams, you're welcome to. I'll record it. So if you don't have time, you can always watch it later. Tomorrow morning as well, 7:15. I'll go over the same morning review worksheet. Okay. Okay, so let me click on this review sheet here. There's still some adjustments I need to make, but this morning review is longer than what you're going to expect on the quiz. The quiz is only going to be 7 parts, front and back. This one has 10 parts. This says 3 pages. But the reason that I made this a little bit longer, just to kind of have you guys do some additional practice, but then also to show all the different topics that I may choose from to put into your quiz. Okay, so and then just like on your quiz tomorrow, I will attach a formula sheet. Okay. So really encourage you guys to go through this. I think you'll really get a good feel as to what to expect tomorrow. Or maybe you even want to do this where you have the notes in front of you, and then you'll work through this like as if it was kind of like a mock quiz, right? And then you can really see where you stand. You know, don't use the key, use the notes that you've gathered, and that way you can kind of create a kind of a quiz environment for you to practice through and see where you stand with this material. Okay. All right. So worksheet 3, worksheet 3 and the homework number 9. This is assignment number 9. Assignment number 8 was what we did on Monday, and those are the last 2 assignments that's going to compose of your quiz grade out of all these other previous assignments. So that assignments 8 and 9, these are the last 2 remaining homework assignments. These will be due into Teams by Sunday. Okay, so I'll create that Teams assignment later today. So any students who want to turn in early, they can, but you have until Sunday to turn in. And then I say homework assignments, but just like before, you're going to turn in your notes and your homework sheet. So it's going to be 4 pages per assignment. You'll be turning in a total of 8 pages for your for this last assignment. After spring break, I'm going to be creating a much more detailed schedule, but we're going to be going through the other common FRQ topics. So if you're taking the May exam, you're going to be doing 6 FRQs. Each FRQ is just maybe like 3 or 4 sections. It's not going to be as long as this FRQ. This is kind of like the quiz you're going to see tomorrow. I kind of combined 2 FRQs into 1 problem. But each FRQ is about you're allotted 15 minutes, and it's about 3 to 4 sections. So just kind of give you an idea as to what we're working towards. And the nice thing is, you know, we still have a month, right? And we're already in review mode. You're already seeing these FRQs, and you know, by the time you see this 2nd, 3rd, 4th time, I think the hope is that you'll feel really comfortable because you've seen this so many times. You've been doing the same problems over and over again. You've seen the same concepts, the same. You know how they're going to ask a problem, and things will be hopefully very familiar in a month's time. So just kind of give you an idea. The most common topics that you're going to see: solving differential equations. So we saw that on the test. I created kind of like a mock FRQ with slow fields, with solving differential equations, with linear approximations. So we can kind of expect that to be a common FRQ. Area, volume, disk or washer method. A lot of you guys did really well on the test, so that's, you know, this should feel, you know, should still be pretty fresh in your mind. But of course, you know, we're going to review through each of these. Derivative graphs, Riemann sums, we're kind of circling around these topics on the quiz, so this is kind of like our focus for the quiz tomorrow. Anti-derivative word problem, we saw a couple of these with the sand being drawn away and added to the beach, like those types of problems. People entering and exiting from amusement park, right? Those are anti-derivative word problems. Particle motion, we haven't seen these yet, but typically these are kind of like on the easier spectrum of AP exams. So I'm kind of focusing on the ones that I feel like we probably need more time to kind of get used to. But we'll do a couple particle motion. But when you see these, it's going to feel easy. Typically calculator questions, but we'll definitely do those. And then I would say related rates is another potential one. But recent years, they've kind of inserted related rates into like part C or part D of another FRQ. I don't see a lot of standalone FRQ for related rates recently, but you know, maybe it's time for one to show up. So you know, we'll practice a few more with these, but I think yeah. So these are the big topics, right? And I'm hoping that as when we come back from spring break, we can kind of do, you know, an FRQ a day, but then we can also kind of hit some of the multiple choice topics, so that, you know, in a month's time or 3 weeks time, you'll feel really good, comfortable leading up to the AP exam. Okay. But then along the way, we also need to get ready for a pre-AP test, which I'm still trying to figure out what the format of that is. So we'll be working towards that as well. But yeah, any questions that you guys have? Okay, let's go to our review sheet. This is the stapled notes here, worksheet 3, but I want you guys to turn to the second page. And if you're on Teams, it's going to be a separate link. It's going to be that second link below notes, FRQ variations. Okay, I want to talk about this because there are two variations that your derivative graph may look like on tomorrow's quiz. And depending on your version, I want you guys to make sure that you're familiar so you can make the adjustments necessary for either type. So the first variation is this. Let's say we have a figure showing f prime, and we're told that it's a derivative of a differentiable function. The areas of the region are provided here. So the first region is an area of 7. Second region is an area of 6. The third region is an area of 8. But because we're dealing with definite integrals, we have to keep in mind that these are going to be positive and negative results depending on whether it's above or below the x-axis. So I'm just going to start labeling them here. So this region here, I'm going to say 7. This region here, I know the definite integral is going to total to be -6. And last one is -8. The last two are below the x-axis, so the reason for the negatives. Right. We're given that they're telling us explicitly this is a derivative graph, but we're trying to find f of -3, and this is part of the original graph that we're not seeing, right? We're only seeing the derivative graph. But the derivative graph will only tell you the accumulation of progress between one point to the next. But if I want to find a physical location, I need to be able to anchor it to a starting point, to an initial point. So if you see the setup where I give you a derivative and a starting point, we got to be able to go through this, this formula here. Final position equals initial plus displacement, and this will be on your formula sheet. Okay. Now let me talk about initial position. Initial position doesn't mean that it's going to be, the furthest left. It doesn't mean that it's going to be starting at this point. The initial point is basically whatever is given. It could be anywhere. It could be any x value along the interval. But whatever is given is your starting point. This is your initial point. Okay. So if I want to find f of -3, I need to figure out where I'm starting from, how much progress I made, and that's going to tell me where I'm going to end up. So I'm going to follow the formula exactly as I see it. My b is -3. I want to find f of -3. My starting point is my given. I'm starting at f of -2. And I need to find how much progress I'm going to make between -2 and -3. So definite integral of f prime. Now let me ask you this. If I follow the rule, what's my lower bound going to be initially? -2. We're going from -2 to -3. I know it's backwards, but initially, just follow whatever the rule says. Okay. If we need to make adjustments, we'll make adjustments at the next step. Okay. So these numbers will always match. Your lower bound and your initial value will always match. Your upper bound and your final will always match. Okay. Okay. Any questions there? Now, we'll take a step back and see, is there any adjustment we need to make? Because we need to finalize what this value is going to be, right? We're trying to resolve this integral with this graph. So what do you notice about the integral that may be helpful for us to adjust? Okay, yeah, negative, and then the reason why you want to put a negative is because why? Yeah, we'll flip the balance, right? Now that I'm looking and trying to connect my integral with my graph, I'm realizing, okay, I want to read the graph from left to right. That way I don't have to keep track of, opposites in my head. I can just write down whatever I see on paper. But now I can adjust the bounds, right? Don't adjust the bounds here. If you adjust the bounds while you're doing the formula, most students miss the fact that they got to change the sign. So follow the rule as you see it, and then adjust if necessary. So I'm going to change the order of the bounds so I can go from smaller to larger. But then as I do that, I need to make a balancing adjustment by putting a negative in front. Sorry, it looks like it's connected here, but that -2 here is for this other integral. Okay, are we good so far? Okay, so everything is nicely set up. Now we can just pull values and replace them with those into these notations that we have. So f of -2, we look at our given, that's just equal to 4, minus, and then the definite integral from -3 to -2, that's just a +7. We can just copy down exactly the sign that we see because we've already made the adjustment because of the fact that we're going backwards. Okay, I made a mistake on my key, but the actual answer should be -3. All right, questions? Hey, if I want to find f of 4, same formula. My endpoint, my goal is f of 4. That's my b value. Again, I'm going to start at -2 because that's whatever is given to you is your starting point. Plus. Okay, what's my lower bound and upper bound? Lower bound is, yeah, -2 to 4. Just following whatever the rule says. Right, so I'm just copying down whatever the rule says, and now I'm going to take a step back and ask, do I need to make any adjustment, or is this ready to go? Yeah, we're ready, right? Lower bound, upper bound, smaller to larger. I'm already going from left to right, so this is good. Okay, we can go directly to our graph and start making our substitutions. F of -2, which is 4. And then -2 to 4 is just these two values combined together. Sorry, I may print these bigger. Putting down exactly what I see, 4 minus 14, -10. Okay, how are we with that? Yes?
Could you explain again, like, for f of -3, why you switched it from, like, you switched the negative to -3 and then you switched the positive into the negative?
Right, so the reason why is because here, if I leave it the way that it is, that means I'm going from -2 to -3. That means I'm going backwards. If I'm going backwards, then this 7 is not really a 7. This 7 is really a -7. So you can avoid, if you don't want to do this, you can just do this on your head and say, okay, I'm going backwards, so that's therefore it's a -7. And I can just say 4 minus 7 is -3. But I find it more straightforward if students just make the bounds go from smaller to larger. But if you flip the bounds, you're changing something about the problem. You're changing the way that you're reading the problem. So anytime you flip the bounds, I'm just going to change that sign. And that way, I've already taken care of the negative, and I can just read the graph exactly as I see it. I don't have to keep track of all these opposites in my head. because I already took care of it with that notation there. Okay. Good. Any other questions? But if your bounds are already in order from smaller to larger, then just leave it alone, right? Typically, right, we only need to adjust. Now, if it's a power rule problem, let's say I gave you let's say you're trying to solve this by hand, and you're going from, 5 to -2. I would say for this problem, there's no need to adjust the bounds. You can just do power rule, plug in your upper and lower bound, and things will just work out the way it's supposed to. You can, but for this, I don't think it's imperative. Well, I don't think it's as important because you're not going to mess. It's, things will just work itself out. But here, being able to look at a graph and being able to pull the information as you see it rather than trying to keep track of all these opposites in your head. So typically I like to flip the bounds if I'm trying to read the graph. But if it's just a problem where I'm doing just power rule, antiderivative, I don't have to flip the bounds. I think you can, but I don't think it's as important to do it that way. All right, are we good with this variation here? Okay, let me talk about this other variation here. I purposely made it almost exact duplicate. It's the exact same problem, but there's an important difference that I wanted to point out. Same graph, same region, same area. But the difference here is that we have this relationship here between g and f. So let me write this up here. G of x is the integral from 1 to x of f of t dt. So this relationship is telling us what how these relate to one another. So right now, I need the integral of f in order for it to be at the same level as g, which means that f is really sitting at that one level below g, which is telling us that f is really a g prime graph. Okay. So this is still a derivative graph, but now this is a g prime graph. Okay. We're still going to treat it the same way. It's just something's a little bit different with the way that things are defined. So you can also think of it in terms of, well, this is also just second theorem going on here, right? If I want to find a derivative, I can just tack on derivative notation. And I know the derivative and integral will just take itself out. The upper bound gets inserted in. So that just becomes f of x. And so g prime is just f of x. So this notation just tells me, okay, I'm basically staring at a g prime graph. Now, if I want to find g of -3, I'm just going to follow this explicit rule that's here in front of me. So if you see an explicit rule, we don't do the final equals initial plus displacement, because we have something that is very specifically defining us what our g of value is. So here we don't add on to a starting point because they're telling us exactly where that point is. So we're just going to follow whatever the rule says. My upper bound is the location of my variable, so that's where I'm going to replace my x with -3. I'm following the rule exactly as I see it, but now that I've followed the rule, I know I have to resolve this with the graph. And what do you notice about your bounds here? Right. I'm going to go ahead and flip it so that makes it easier for me to read the graph. So change the sign, adjust the bounds. And now I can see, okay, I'm just going to total whatever region I see between -3 and 1. And that's just these values here. 7 minus 6. Keep the negative outside so we don't lose track of it. 7 minus 6 exactly the sign as we can expect from them. And then 7 minus 6 is 1. We keep the negative, so therefore negative 1. Okay, let's find g of 4. Again, following the rule exactly as we see it here. Lower bound is 1, upper bound is 4. Oh, don't worry about the fact that these are different variables. It's because of notation, because my upper bound can't be the same variable as that. So you don't need to just know that, you know, you're just basically staring at the same graph. Okay. So I follow the rule. Do I need to make any adjustments, or the bound's looking good? Yeah, looks good, right? Smaller to larger, no need to adjust. Read the graph, just -8. Okay, any questions? All right, so the recap. If I give you a derivative graph and I don't give you a specific rule or a specific formula, then you have to rely on this final position equals initial plus displacement. Okay. But if I give you something like this, where there's the explicitly defined, then you're still looking at a derivative graph, but you're just going to follow whatever this rule says. Don't attach anything else to it. There's no plus initial or minus displacement. You're just going to rely on this to find your order pair. Yeah.
These are going to be associated with word problems, though, right?
I'm sorry?
Are these going to be associated with word problems?
Typically, I've seen these. I've seen kind of like a variation of this show up on a multiple choice question. But yeah, if it's in relation to a derivative graph, it's going to be on like an FRQ. Yeah. So typically your derivative graph kind of falls into these two camps, where either they just tell you as f prime and given, or specifically defined. But I want to make sure that you guys are clear on that distinction, so whichever version you see tomorrow, you know how to find order pairs involved. Okay, questions? Yeah, so I think that the morning review is good place where everything is kind of put together. So you can kind of see it all played out exactly as I'm going to be asking it tomorrow. Okay, let's go to the front page here, worksheet 3. Okay, we're just circling around the different types of problems that you're going to see tomorrow here. Okay, f and f prime are differentiable functions. Value of f and f prime are given. G of x equals f of x squared. Find the instantaneous rate of change of g at x equals 9. So, what is this saying?
So f prime is 9?
Close. G prime, right? G prime of 9. Yeah. Yeah. Find G prime of 9. Yeah, just a fancy way of saying, tell me the slope at that point. So before I can find G prime of 9, I need to find G prime of x. To find G prime of x, look at how this is set up. What's involved here? Chain rule, right? Good. Chain rule. So I'm going to rewrite this to maybe make it a little bit easier for us to see that distinction, because chain rule is required if there's an outer and inner portion of our problem. So I'll use bracket here to make it more obvious there. We got that bracket squared, and we have that f of x. Okay, so my outer portion is that bracket squared. My inner portion is that f of x. And we're just going to take turns with each derivative. All right, so first things first, that bracket squared. What's bracket squared's derivative?
2 brackets.
Yeah, 2. It's like power rule, right? If it's x squared, you'll say 2x to the first power. If it's bracket squared, you'll say 2 bracket to the first power. We're just treating that bracket like if it's its own variable. I'm not going to make any changes with my inside, so I'm just going to fill that space in with the original inside. So that takes care of my outer derivative. What's my inside function's derivative? F prime of x. So notice we did power rule for one, and then we just did function notation for the other. So AP exams, they love to do this on the FRQs where they mix function notation with expression, and you have to kind of work your way through it. Okay, questions so far? Okay, we're done with the calculus. Now we can just insert 9 in for all the x's. Okay, we have a table of values, right? So we can find the appropriate values for f of 9, find the appropriate value for f prime of 9, and just insert them into our answer. So we have f of 9 here. We have f prime of 9 here. Okay, so 2 times -2 times -4. Okay, -4 times -4 is 16. Okay, any questions there? Okay, part E, or sorry, next part C here. K of x equals f of 3x times x squared plus 1. Find the slope of the line tangent to the graph of k at x equals 3. What is this asking for us to find?
Just the tangent line slope, I guess.
Yeah, so it's basically asking the same thing as part A, just worded differently, right? So we're just going to find k prime of 3. So before we can find k prime of 3, we need to find k prime of x. To find k prime of x, what's involved here?
Product.
Okay, product rule. So that's the main one. What else do you see?
Would it be also chain rule?
Yeah, there's a little bit of chain rule. Yeah, just only a portion of it, but there is chain rule occurring here. All right, so let's set up that product rule part here. All right, so chain rule is within this little f of 3x, right? So let's do a little bit of spelling out the parts that's going to create the full derivative there. So I know with that f of 3x, there's the outer portion of just that f parentheses, and there's the inner portion of just that 3x. So we need to involve both these features in order to create our full derivative of that f of 3x. So take turns. What's f parentheses derivative?
Would just be f prime.
Just f prime, yeah. Keep the inside intact. That takes care of the outer derivative. Now move on to the inside. What's 3x's derivative?
3.
Times 3. So that, both of them will create the full derivative that we need for f prime of x, or for this first term's derivative. We'll copy down the g function as is, no changes there. Back to f, no changes. times, okay, what's g prime going to be?
Just 2x.
Just 2x. X squared becomes 2x. 1 goes to 0. So we're constantly adjusting the way that we take derivatives, right? If this is function notation, sometimes we got to do some chain rule. Sometimes it's product rule, right? So everything is, everything's kind of worked into very compactly into this problem here. Really showing if we can understand and kind of maneuver through all these different things we got to keep track of. Okay, questions so far? Okay, so the calculus is done. Now we can worry about the value. Replace every x I see with 3. Again, table of values helps us make these final sets of substitutions. Use your calculator if you like. This ends up giving me negative 120 minus 12. Okay, any questions here? All right, let's look at part D. Evaluate the definite integral from 0 to 3 of f double prime of 3x. So two things going on here that I want to point out. The first thing is, you see how there's a function within a function? For derivatives, we call this chain rule. But for integrals, we have we call it use substitution. So there's no chain rule for integrals, but it's kind of like two sides of the same coin here. We're just kind of undoing chain rule with use substitution. And the second thing that we have to keep track of is the fact that there's something that's being done to that f double prime. So there's a little bit of first theorem here. So let's just explore that relationship here. If I have f double prime of x, what's going to happen to that f double prime if I push it through the integral process?
Just becomes a prime.
Right. So I think we're really comfortable with derivative features. If I ask you for derivative of f, you know to go to f prime. Derivative of that, you'll call it f double prime. But the integral procedure, we also need to make sure that we're comfortable with, that we're just moving back up the chain where we came from with derivatives. So f double prime, antiderivative, we're going to undo that derivative. We're going to move up to f prime. And then we can work in our bounds. Okay, so we're going to involve both these features in our problem. So let's start with use substitution, right? We know that our first goal is to figure out what's going to happen with that 3x? After we clean this up, is there any coefficients that we need to keep track of? And that's what is going to help us. We're trying to get this cleaned up because right now it's a little bit more involved than what we would like. If it was just f double prime of x, then we can just go forward and take the integral. But that 3x, we need to know what's happening with that inside portion. So u equals 3x. du dx. Cross multiply here. Solve for dx. Replace our underlined portions with, in terms of u, don't copy the bounds just yet, okay? We'll just take care of that integrand. So you see how cleaned up this gets here? We're able to get this down to one variable. We're able to get that cleaned up here. But this allows us to know we got to keep track of what? Yeah, there's that 1/3. That u substitution allows us to know that's going to be part of our antiderivative. Okay, so now I can apply directly with first theorem. Everything is cleaned up. F double prime is going to work its way up to f prime. Don't forget about that 1/3. Okay, so we have our antiderivative. Now we can worry about what to do with the bounds, right? The bounds are now going to play a role in helping us get down to a numeric answer. Okay, questions so far? I know I have to involve bounds somehow. Can I use the 0 and 3 with what I have here? Why not?
Yeah, they converted it into what you got.
Right. Either one of two things. Either you get everything in terms of u, or you get everything in terms of x. But you don't want to mix u and x because then we're not dealing with the same thing here. So I'll go through method 1 first. You can write both of these methods down for now, but on the quiz, you just choose one and you just pick whichever one you want to do. So method 1 is converting everything in terms of u. So convert the bounds. Okay, so my old x lower bound is 0. My conversion is through that u equals 3x. So u is equal to 3 times 0. Okay, so it looks like it ends up giving us the same lower bound, but we still have to make sure we went through that conversion process. My old upper bound in terms of x is 3. Which is now 9. Okay. Now I have a consistent variable here, right? Bounds are in terms of u, my antiderivative in terms of u. Now I can plug in. Upper bound first, followed by lower bound. F prime of 9, we go to our table. F prime of 9 is just -4. F prime of 0 is just -3. So negative 4/3 plus 3/3 is negative 1/3. Okay, so that's one way to do it. Second method, which I think a lot of students prefer, which is fine, is taking the antiderivative and then just getting this in terms of x, and then just use the original bounds. So just bring that u back in terms of x. My x is 3x. And then if you do that, then you can just rely on the original bounds. There's no need to convert the bounds. Upper bound first. 3 times 3 is 9. Minus lower bound, 0 in for x, 1/3 f prime of 0. And we're back to where we came from. So either method is fine. We'll get the same answer. Whichever method you choose, we just don't want to insert the 0 and 3 into f prime of u. Okay, that we're not going to get the right answer that way. Okay, any questions? I want to just pick just a little bit from the homework 9 that you guys also picked up. Just want to, won't have time to do it all, but just want to kind of start that process a little bit here. Okay, no questions here. Okay, this is off the homework 9 worksheet here that you guys picked up if you're in class. It says the function is continuous. Okay, Paul is asking, how did you get from f double prime to f prime? Okay, let me go back to that. The reason that we can get from f double prime to f prime is because we're making it go through the antiderivative, right? We're making it go through the antiderivative. And that just goes along with first theorem that tells us that if your derivative takes you from f prime to f double prime, then your antiderivative will bring you up the chain. It'll allow you to move between derivatives, but then now we're going the other direction. So remember, antiderivative is the opposite of derivative, right? It's in that name, antiderivative. We're undoing our derivative process. Did that answer your question, Paul? Okay, let's do it just with our time available here. Okay, from -2 to 7 is our region. We got a semicircle, a triangle. It says find g of 2. So g of 2, we're just going to follow the rule here, right? There's no need to do final equals initial plus displacement because everything is defined within this rule here. Two squared, we plug in 2 in for x, 2 squared is 4. So these are nice geometric shapes. We're just going to find the areas of these regions that we're working with. Oh, I'll just do the first two regions here. We got semicircle, so 1/2 pi r squared. All these formulas will be on that formula sheet. My radius is just going to be 2, right? Center to a point on the circle, on the semicircle, equals 2 pi. Triangle, 1/2 base times height. My base is 2, my height is 2. So once I follow the rule, I see that my bounds are in the correct order. I can just read the graph exactly as I see it. No need to flip the bounds because I'm not having to read this backwards. So -2 to the 4, semicircle plus a triangle here, so 2 pi plus 2. They're both above the x-axis, so I can keep them both as positive. Okay, g prime of 2. Before I can get to g prime of 2, I'm going to create what g prime of x is because I got to do something with that x squared there. So I need to involve the derivative of this integral. And as a reminder, this is basically second theorem. So second theorem says this. I'll put it in red so you can see what the rule says. If I'm going from a to p of x of f of t, what's going to happen is this upper bound is going to get inserted into that variable. And then I also need to involve the upper bound's derivative. Before, we didn't do anything with it because it was just x. X derivative is 1, so it didn't produce anything. But this x squared, if your variable bound is more than an x, then there's going to be some left over. So x squared becomes 2x. Okay, so that's the rule here. So if I want to find g prime, upper bound gets inserted just like how we have the rule here. Times p prime, so times my upper bound's derivative here, so times 2x. So g prime is simply f of x squared times 2x. So if I want to find g prime of 2, I'm just going to follow whatever the rule says. So g prime of 2, it's just going to be f of 4 times 4. F of 4, I just need to pull information from the graph. And f of 4 is simply 0. That's just the x-intercept there. Okay. I created a video for homework 9, so if you want to work through the rest of this, you can check the key as well as you can watch that video. But this afternoon, I'll be doing a help session on Teams, 4 to 5 p.m., going over the Sunday morning review. Going over the morning review. I'm still working on that worksheet, but it'll be ready for you to access by this afternoon. So really encourage you guys to work through it. I think that's the best way for you to prepare for that quiz tomorrow. If you can get through that morning review, you should feel pretty good about the quiz. All right, thanks everyone. Study for your quiz. Hopefully I'll see you in the help session. If not, I'll see you tomorrow. Thank you. See you guys.